Hello, George Romanich here. Behind me over here you can see a wall, just like wall in your room. How many atoms of air that we breathe hit this wall every second? That's what we are going to explore today. Here is a wall of your room. And there are a lot of atoms and molecules of air in your room, hopefully. Let us say this is positive x direction, and the area of this wall is A. How many of these particles that are moving in every given direction is going to hit your wall? Well, say that there are n particles in your room. In time delta t, only those atoms that are moving towards the wall and are this far away from the wall will hit the wall. Now the question is, what is this far away? Well, clearly this distance that I called this far away is Vx delta t. But because this is of course three-dimensional space, the wall is going, into the page, we have to find the volume of the space that contains atoms that will hit your wall. So the volume, capital V, let's call it volume of the hit, is equal area of the wall times this distance over here, which is Vx delta t. But we know from my previous video on Maxwell-Boltzmann distribution that it is not true that all atoms have velocity Vx. Some are moving slower and some are moving faster, as I indicated here with the length of these arrows. Some arrows are longer, some arrows are shorter. The distribution of their speeds is given by Maxwell-Boltzmann distribution. And in one direction, and we are interested in one direction, x direction, because that will bring this atom in the collision with the wall. Let's say this is the speed, but only component of that speed towards the wall will bring this atom in the collision with the wall. And the distribution of speeds based on Maxwell-Boltzmann law in one direction, so here is f of v of x and here is vx, has this nice Gaussian shape. The distribution is symmetric around the y-axis and the most probable speed is 0. So instead of volume of the hit, what we need to find indeed is the average volume of the hit. Because, why average? Well, because, as I just said, as you can see here, some atoms are moving slower and some atoms are moving faster. And the average volume, therefore, will be A times delta t. And to account for distribution of speeds rather than one speed, we find the mean speed from this distribution, and that would be, of course, Vx f of Vx dVx. But now we just said the most probable value is 0. Yes, it is if we are looking into both negative components of the speed and positive components of the speed. But in our particular problem, we are only interested in positive components of the speed in the positive x direction because only those will result in collision with the wall. If we have this atom over here that is moving in that direction, who cares? That one is going away from the wall, it's not going to collide. So this distribution cannot be integrated from negative infinity to positive infinity, but rather from 0 to positive infinity, because only these atoms will result in the collision with the wall. That should be logical. But we know this distribution from my video on Maxwell-Boltzmann distribution. We know that f of Vx is equal square root m divided by 2 pi kt e to negative mvx squared divided by 2 kt, where m is mass of these atoms, T is absolute temperature in Kelvin, and K is Boltzmann constant 1.38 times 10 to power negative 23 joules per Kelvin. Combining this with that, we get that the average volume of the heat is equal A times delta T times this constant square root m divided by 2 pi kt integral between 0 and positive infinity, and we have this Vx, and multiplying this exponential term e to negative m Vx squared divided by 2 kt dvx. How does one solve this integral? Well, we introduce a substitution, or on this channel we like to use quick and dirty method that I introduced in one of the previous videos. And the quick and dirty method says that, look, this Vx dvx I can write as 1 over 2 d of Vx squared, because when I carry out this differentiation I'll get this, which means that this integral, if I call it I, will become integral between 0 and infinity. Vx dvx is 1 over 2 e to negative mvx squared divided by 2 kt dvx squared. And now this is just like integral e to negative x dx, because here we have x squared and we have dx squared. The solution of this integral is, of course, minus kt divided by m, because m goes downstairs, and this 2 cancels with this 2, e to negative mvx squared divided by 2 kt, and of course the limits of this integral are between 0 and infinity, or this is further equal negative kt over m. What are we going to have here? Negative infinity, that's going to be 1 over e to infinity, forget about these constants, minus 1 over e to 0. And what is this equal? Well, this tends to 1, because e to 0 is 1, and this clearly tends to 0 because 1 over infinity is 0, so I will get this minus, and this minus will give me plus kt divided by m. Or now going back to the beginning where everything started, average volume of the heat is equal A times delta T times square root m divided by 2 pi kt, and times this guy over here, kt divided by m. Or now you can organize this to look nicer, and we conclude that the volume of the heat is equal A delta T square root, let me see. So this should be kt divided by 2 pi m. But at the end of the day, we started this video saying what is the number of atoms that will hit the wall, not what is the volume that is containing these atoms. How do we get from volume to the number of atoms? Well, we use equation for ideal gas that says that pressure in the gas times volume of the gas is equal number of atoms in that gas times Boltzmann constant times absolute temperature. Or from here, if I apply this to the volume of the heat, I can see that number of atoms that will hit the wall is equal pressure times this average volume of the heat divided by kT. In other words, what I'm saying here implicitly, this is ideal gas law. It works for any gas, any volume, and any temperature and pressure as long as we are, in the kinetic theory of gases. So if it works for anything, well, then it's going to work for the volume of the heat. So I am applying it to the volume of the heat. Or now combining these two together, I will get that number of atoms that hit the wall is equal A times delta T divided by kT and times this pressure as well, and this square root kT divided by 2 pi m. Or the number of hits per area and per time interval delta t would be number of hits per area A and per time delta t is really equal P divided by kT square root kT divided by 2 pi m. If we take that delta t is 1 second and area is unit area of 1 meter squared, then notice that this represents collision frequency that is equal this, but I will now make this a little bit better, and I will say this is P divided by square root of 2 pi m kT. And this is the beautiful result. Of course, sometimes people would look into this and say, yes, but what if I don't want collision frequency in 1 second and 1 square meter, but if I want in 11 seconds and 23 square meters? Well, multiply this result by your 11 seconds and 23 square meters, and that's it. But collision frequency, and of course any physical variable, is generally given per unit time, per unit space, per unit volume, and so on, whenever possible. And then you can adjust to time, volume, space of your interest. And I just told you how you do it in this case. So let us say that we are in your room and we identify this wall of interest. Pressure in the room is 1000 millibars. And that is, of course, 10 to power 5 pascals, because you have to use pascals here. Temperature in your room, it's very comfortable, it's 23 degrees Celsius. And that should be 296 kelvins, because you have to use kelvins. And we are interested in, let's say, nitrogen atoms hitting the wall of your room. Nitrogen is 78% of air. And I found on the internet that mass, because we need mass, of a nitrogen atom is approximately 4.65 times 10 to power negative 26 kilograms. So if you plug in these values in the formula And if you don't know what the pi is, then close this video and go and watch beauty bloggers. If you carry out this calculation, you will get that collision frequency between nitrogen atoms in your room and 1 square meter of your room in 1 second is equal 2.9 times 10 to power 27 collisions per square meter and per second. Now, if this is not breathtaking result, then I don't know what could it be. Atmosphere is absolutely beautiful, and we live surrounded by air, never thinking what is going on around us. And what is going on is that atoms of nitrogen are bombarding 1 square meter of your room this many times in 1 second. The beauty of kinetic theory of gases and atmospheric sciences becomes even larger if you think that we calculated this number by knowing only macroscopic properties of our gas, namely pressure and temperature. Here is a wall. We discovered that every second 10 to 27 particles of air hit 1 square meter of this wall. The same happens in your room. 1, 2, 3, 4. Every second of this counter, approximately 10 to power 27 atoms of air collided with that wall over there. And the same happens with any wall in the basement, any wall in toilet, any wall in a shoebox, walls in our lungs, and so on. Kinetic theory of gases is an amazing theory, and atmosphere is an amazing medium. When we put these things together, we can visualize things that we will never be able to see. And one of these visualizations is today's video. Now go and look into the wall. I do it every day. Look into the wall and imagine how many atoms are hitting that wall every second after second. Until next video, goodbye.